Hello, welcome to Unit 2, Lessons 12, Using Graphs to Compare Relationships. For this lesson, there are two learning objectives. The first one is to be able to compare two related proportional relationships based on their graphs, and to also be able to know that the steeper graph of the two proportional relationship has a larger constant of proportionality. Now, in the last lesson, we focused on more proportional relationships with graphing. We revisited the idea that graphs of proportional relationships are linear, so they're a straight line, and they pass through the origin. We also talked about how the constant of proportionality shows up in the graph as a point on the line. That point is always 1, comma, and then the constant of proportionality. So let's go ahead and get started with the first activity. This first activity is a number tuck, which unfortunately we're not able to do together. So go ahead, what I would like for you to do is pause the video and find the product of the very first problem, 2/3 times 1/2. Once you find that product, go ahead and restart the video. All right, so there's a couple of different ways you can look at 2/3 times 1/2. Okay, one way is that you just multiply straight across, right? 2 times 1 is 2, and 3 times 2 is 6, and then 2/6 simplifies to 1/3. Okay, that's one way of doing it. Another way of doing it is thinking about what this actually means. So what we're doing is we're literally taking half of 2/3. So if we were to split 2/3 in half, we would get 1/3, right? Because 1/3 plus 1/3 is 2/3. So that's another way of looking at it. So go ahead and pause the video and try the second one. All right, let's take a look. So this next one, we have 4/3 times 1/4. There's a couple of different ways of looking at this. You could, again, just multiply straight across. 4 times 1 is 4. 3 times 4 is 12. And then that simplifies to 1/3. Another way of looking at this is if we were to take 4/3 and split them up into groups of 4s, we would have 4 groups of 1/3, right? 1/3 plus 1/3 plus 1/3 plus 1/3, that's equal to 4/3. Now, 1/4 of that is just going to be one section right here. So, right, we're talking about 1/4 of 4/3. Well, that's going to be equal to 1/3. Go ahead, pause the video again, and try the next one. All right, next one is now we're dealing with division. Now, in the past, you may have learned such tricks as flip and divide, things like that. But I try not to go with just the tricks. So instead, let's think about if we were to actually divide this, what it looks like. So division kind of works in a similar manner as multiplication does. So we could potentially just divide straight across, right? We could take this 4 and make it a 4/1 and have 4 divided by 1 and then 1 divided by 5. The problem with that, though, is that we can't really do 1 divided by 5. So instead, let's change this fraction so that we can divide something by 5, right? What number is easily divisible by 5? Well, 5 is easily divisible by 5. So I'm going to take this 4/1 and I'm going to make an equivalent fraction where the 5 is the denominator. So to do that, I'm going to multiply by 5/5. Well, when I do that, I get 20/5. So now I have 20/5 being divided by 1/5. So again, we can just move straight across. 20 divided by 1 is 20. 5 divided by 5 is 1, and then we have 20. Another way of looking at this is if you were to take 20/5 and imagine those being split up into groups of 1/5, you would end up with 20 sections. So another way is just to envision this 20/5 being split up into groups of 1/5 to get the 20 sections. All right, go ahead, pause the video, and complete the last problem. All right, so next one. Again, you could use the method we used previously and just divide straight across. 9 divided by 1 is 9. 6 divided by 2 is 3. And then 9 divided by 3 is 3. You could also think in terms of if I had 9/6 and I simplify 9/6 to 3 over 2, and if I were to split these into groups of 1/2 in size, so if I had, 3.5, that looks like this. So 1, 2, then we have 3. So those 3. And if I were to split them up into halves, which they already are, how many would I have in total? Well, I would have 3 in total. So that's where the 3 comes from. So that was our warm-up, our altered number talk. So let's go ahead and move on to the next activity. So in this next activity, we're going to kind of think back to the last lesson where we were looking at Tyler and his walking to the bumper cars from the ticket booth. This time, we're going to add Diego, Lynn, and May to the situation. So let's go ahead and take a look at the problem. So it says, use each description to complete the table representing that person's journey. So Diego left the ticket book at the same time as Tyler, but Diego jogged ahead at a steady pace and reached the bumper cars in 30 seconds. Now, if we take a closer look at Diego's table, we can see that 30 seconds being represented in the 50 meters, right? So it took them took Diego 30 seconds to go a total of 50 meters. Now, Lynn left the ticket booth at the same time as Tyler as well. She ran at a steady pace and arrived at the bumper cars in 20 seconds. So if we look at Lynn's, we can see here it took her 20 seconds to go a total of 50 meters. May left the booth 10 seconds later than Tyler. Her steady jog enabled her to catch up with Tyler just as he arrived at the bumper cars. So she left at 10 seconds later than Tyler, so that means it took her a total of 40 seconds to go 50 meters. So what it wants us to do is finish completing the table. So let's start with Diego. Now Diego at 0 seconds, he was 0 meters. He didn't travel. Okay, now if it took him 30 seconds to go 50 meters and he was running at a constant pace, that means there is a constant of proportionality. So to figure out that constant of proportionality, I need to take my y and divide it by x. So that means I'm going to do 50 over 30. But when I divide that, notice you'll end up with a repeating decimal, and we can't work with repeating decimals. So instead, we're just going to simplify this to 5 over 3. So my constant of proportionality is 5 over 3. So to figure out how far Diego went in 15 seconds, I'm going to take 15 and multiply by 5 over 3. And when I do that, I get 25. So in 15 seconds, he went 25 meters. Notice the last entry is a 1. Now, in the last lesson, we talked about how the 1 in a table is connected to the constant of proportionality. So I know without doing any kind of math that this is going to be 5/3. So he went 5/3 of a meter. Let's look at Lynn. Okay, now Lynn, again, she left at the exact same time as Tyler, so that means at 0 seconds, she went 0 meters. Okay, to figure out how far or how long it took her to go 25 seconds, I again need to figure out the constant of proportionality. So I'm going to do y over x, and when I do that, I get 50 over 20. This time when I divide, though, I don't get a repeating decimal, I get a terminating decimal. So it's okay to use that decimal. So I get 2.5. Now, I need to go in the opposite direction, right? So that means instead of multiplying by 2.5, I'm actually going to divide by 2.5. So 25 divided by 2.5 is 10. So that means it took Lynn 10 seconds to go 25 meters. Again, notice we have a 1 as our last entry, so I know the number connected to that is the constant of proportionality. So without doing any math, I can go ahead and put the 2.5. Now May is going to be a little bit different, and the reason for that is because she doesn't leave right away, right? She actually ends up waiting for 10 seconds before moving to walk to the bumper cars, and she waits a total of 10 seconds. So that means she's not at 0 seconds at 0 meters, it's actually 10 seconds at 0 meters. Now, because May did not leave right away, we have to look at her numbers for her time a little differently. So although it took her 40 seconds to get to the bumper cars, she really only walked for 30 of those seconds. So when we set up our ratio, it's actually not going to be 50 over 40, it's going to be 50 over 30, which again simplifies to 5/3. So to figure out how long it took her to go 25 meters, I again am going to divide by 5/3. So 25 divided by 5/3 is 15. So that means it took her 15 seconds to walk 25 meters. But here's the thing, she didn't start walking right away. So now that means we have to add the 10 seconds she waited. So really it took her a total of 25 seconds to go if we also include the elapsed time where she waited 10 seconds. So once she started walking, it took her 15 seconds, but it took a total amount of 25 seconds. Okay. Now, the other parts that's different is where was Mai after 1 second? Well, we know she didn't walk for 10 seconds, so that means she hasn't moved yet after 1 second. So this is where you notice 1, 0, there's no constant of proportionality. So that should kind of give you a hint as to whether or not this is a proportional relationship. All right, so let's go ahead and take a look at question 2. Now question 2 says, using a different color for each person, draw a graph of all 4 people's journeys, including Tyler's from the other day. So I'm going to go ahead and I'm going to start by graphing Tyler. Now, Tyler started at the origin, and it took him 40 seconds to go 50 meters. So the origin represents the ticket booth, and then I'm going to plot the point 40, 50, which is right here. So this line here represents Tyler's walking. So I'm going to go ahead, draw a line that connects Tyler. So there's Tyler. So this is Tyler. All right, I'm going to switch to red for, let's do Diego next. So Diego, again, started at the origin, but it took him 30 seconds to go 50 meters. So I'm going to plot that point as right here. So that there is Diego. So I'm going to go ahead and connect that with a point. So again, there's Diego. So this is Diego. Okay, next was Lynn. So I'm going to use green for Lynn. Lynn, again, started at the origin, right? She left at 0 seconds. She was 0 meters. And it took her 20 seconds to go 50 meters. So this is Lynn right here. I'm going to go ahead and connect her. So that is Lynn. And then finally May, which I'll do in black. She didn't start at 0, 0. She actually started at 10, 0, which is right here. But she met up with Tyler right here. So it took her, after 40 seconds, she caught up to him. Oops. So let's go ahead and draw her line. So that was May. Now, if we look a little bit closer at these graphs, we notice that Lynn, Diego, and Tyler, they all show a proportional relationship. It's a straight line and it connects to the origin. And kind of like what we hinted at in the tables, May's does not show a proportional relationship, right? Hers does not start at the origin. So May is not moving, although May did run at a constant rate, it's still not proportional because she waited 10 seconds before she started running. If we wanted to take a closer look at what each of these constants of proportionalities were, we could plot them on the graph. So let's focus on Lynn, Diego, and Tyler. So we found that Tyler had a constant of proportionality of 1.25. So if I look, that's probably right about there. For Diego, his constant of proportionality was 5/3, and that probably shows up about right there. And then finally, Lynn's was 2.5, so Lynn's about right here, okay? So if you were to look at the constant of proportionalities for each of those three people, notice that Lynn's constant of proportionality is the biggest. So that means Lynn moved at the quickest. So when it says number 3, which person is moving the most quickly, we would say Lynn moved the quickest. And there's a couple of ways you can look at this. All right, we could see the constant proportionality is higher. And let's also take a look at the overall graph. Notice Lynn's graph is much steeper than Diego's and Tyler's. So anytime you see a steeper graph, that means that the constant of proportionality is going to be bigger. So in this case, since we're talking about speed, Lynn is going to be moving at the quickest pace. So keep in mind, we only really were comparing Lynn, Diego, and Tyler because those were the 3 proportional relationship. May did walk probably faster than at least Tyler, but it's kind of hard to tell who she walked faster than as far as Diego or Lynn goes. So we're just going to focus on the 3 proportional relationships. All right, let's take a look at the next activity. So in this activity, it says meteoroid Perseid 245 and asteroid X travel through the solar system. The graph shows the distance each traveled after a given point in time. Is asteroid X traveling faster or slower than Perseid 245? Explain how you know. So if you look at our graph a little bit closer, we can see we have time on the x-axis and distance on the y-axis. So that means if we were setting up a ratio of y over x, we are looking at the distance over time. So how far did it travel per single minute, hour, second, depending, we're not 100% sure what exactly we're measuring. So we're looking at speed. This is the speed. Now, in the previous activity, we talked about how lines that are steeper are going to have a bigger constant of proportionality. And let's take a look at that real fast. Let's say we wanted to plot the constant of proportionality on these graphs. So constant of proportionality is where the line crosses 1 on the x-axis. So if I were to draw a line going up, I would see that the asteroid crosses here, where per side crosses here. So that tells me the asteroid X is going to have a bigger constant of proportionality. So bigger constant of proportionality. So if we're talking in terms of time and distance, that means the asteroid X went farther in the same amount of time than per side 245. So therefore, we know asteroid X is traveling faster. Okay, we know this because it went farther than per side 245 did at the same given time. So at 1 second, asteroid X was farther than per side 245. Let's look at question 2, which says the graph shows the price P of different lengths of 2 types of rope. So we have length on the x-axis and price on the y-axis. So again, if I'm calculating the constant of proportionality, which is y over x, I'm calculating the price to the length. Okay, so it wants to know if you buy $1 of each kind of rope, which will be longer. So this time we're going to look at it a little bit differently. Normally we would look at y over x because that's typically how we calculate the constant of proportionality, but it doesn't want to know how much does it cost for 1 centimeter, meter, whatever of rope. It wants to know when it's $1. So instead of looking on the x-axis, I'm actually going to look on the y-axis. So let's say 1 falls about here. If I were to draw a horizontal line across, I can see that the cotton rope falls here and the nylon rope falls here. So that tells me if we're looking at the length, this tells me that I am going to get more nylon rope for $1 than I would cotton rope. Okay, so in this case, we're not going to be looking at the x-axis, we're going to be looking at the y-axis. So the nylon rope is longer because the graph shows a greater length of nylon rope for $1. Okay, so you have to make sure you're reading the question very carefully and making sure you're identifying, are you looking at the x-axis or are you looking at the y-axis? So that's all for today's lesson. Make sure you download the cool down, complete, grade, and correct that, and then do the same for the practice worksheet as well. Thanks for watching.